thinking about whether or not your mind exists is pretty solid evidence for the fact that you think and you exist.
In terms of set theory.
That's what really the card says.
Yeah, I'm sorry. If it's not in sets, I don't know that I can parse this.
Well, except the type 2.
Okay, the set of all known minds.
All right.
Ben Webster.
Yeah, exactly.
Okay, got a little too philosophical up in the front row here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's still 30 people enrolled in this class. Okay. Welcome to SHA256. How was macros? Did you all hate the grader because you didn't look up how it worked? That's on you. I have had the unrelenting and unmatched joy of running other people's code that was undocumented for decades. I would never deprive you of that. Is that me? No. Okay. The great thing about all the code I write is that it's self-documenting, which is not true for code that other people write. Did y'all learn to document your code in 100-level classes?
Yeah.
Did I take those classes? Nope. Okay. I might get you a 1-week extension on SHA256 because I'd like you to actually do it. I'm worried you won't do it if I get you a week. The way I'm going to do that is I'm going to make the Portland crowd go to this Linux user group so I can learn what Flatpaks are. The only thing I know about Flatpaks is Firefox is one. Is that right? Does anyone use Linux?
No.
Yeah.
There is a Firefox spot.
What else is a Flatpak?
Steam, usually.
Steam?
Yeah.
Steam?
Getting Steam to work on different Linuxes is really annoying.
Sorry, did you ask a question?
What is a Flatpak?
It's a container with a graphical interface, I think. I was going to go to the talk. I'll tell you when I come back. Because, like, what's the difference between a browser and a command line utility other than that one of them is good, right? One of them has a GUI. So, I reserve the right to extend the SHA deadline by up to 1 week, depending on how my discussions go with the grads. In exchange for that, I'm going to have a correspondingly higher standard of excellence. SHA256 is perfectly falsifiable. There are 2 different implementations of it on your actual existing physical device, and you only have to compare against those. It is completely deterministic. It is perfectly documented. It is an open standard. The only way this thing can go wrong is if you don't plan ahead far enough, and arguably, if I was bad enough teaching you in earlier classes, then you won't be able to do it in time. The difference between successfully doing something like SHA256 and successfully doing something that isn't real should be fairly immense with regards to your sense of self-satisfaction and the relevance of this course. This is one of the first real things you can do. Speaking of SHA256, what is that? Well, clearly it's 3 alphabetical characters followed by 3 numerical digits. So we already know what that is. What is it? It's basically an algorithm. It maps longer bit strings into shorter bit strings. And how does it do that? In the most painful manner possible, specifically so that it is very difficult to do something that looks an awful lot like SHA256 without actually doing it. The way I think of SHA256 is I'm going to get 512 bytes out of this thing, or 256, I don't know, we'll check the slides. And each bit has no correlation with any other bit. I think of it really strongly as being an output of a probability distribution that's meant to not leak information. So we'll look at that. The slides today are from Saravanan Vijayakumaran, who is the only person in the world that has ever successfully explained SHA256 to me. Maybe they're in here somewhere. Does this say SHA anywhere? No, that's not it. Maybe it's blockchain? Anyway, somewhere in here the slides are good. Anyways, if I were you and I wanted to understand number theory and cryptography, I'd just go through these slides on my own and stop coming to class. Okay, you didn't hear that. Everyone strike that one from the record. All right, this person teaches at the Indian Institute of Technology in Bombay, which, unless you go to the Americans for your university ranking, is better than every university in this country. Okay. Okay, what is a hash function? Do you all know what a hash function is?
Read real quick, see the slide with the person's name on it again, so I can finish writing it down.
Yeah. The URL is easier because it's just Sarva. Electrical Engineering, Indian Institute of Technology, Bombay. I don't know what AC is. I think it's academic, and then it's the India extension, and then Sarva. So it's not too hard to remember. I was following this person's slides for years before I learned who they actually were. I was following one of their former grad students that came to the United States. And I was like, wow, these slides are so good. And I finally found the source earlier this year. And it turns out the original ones are better than the ones I was following, actually. Okay, what are we doing? Okay, so we all love operating systems, right? We download them all the time. We run them on our computer. Sometimes we run games inside of them. Sometimes we run flat packs inside of them, even if we don't know what flat packs are.
Sometimes we run games inside of flat packs inside of them?
Sometimes we run flat packs inside of games inside of them. Yeah, when I wrote a computer inside of Terraria and downloaded SteamOS onto that computer, and then I opened a flat pack inside of Steam on my Terraria, running inside my Steam, running inside my flat pack, running inside a Podman container on a Kubernetes cluster hosted on Google Cloud that I SSH'd into from my cell phone, running an Android system, emulating iOS. Okay, so how do we tell if a hash is good or not? Well, that depends on what you're using it for. I will tell you what SHA256 is used for. It's used for integrity. Integrity is our first vocabulary word of this term. Everybody say integrity.
Integrity.
Integrity means we can have confidence that the bits in something we're downloading off the internet wasn't messed with. Usually it's referred to as data integrity. It's usually the data that's not changed. Now, fortunately, because in the von Neumann architecture we have correspondence in between memory and executable code, this also means we can be confident in executables. An example of something that can be executed is an operating system. Okay, so how does this work? There exist bits that float around in the ether, and sometimes I slurp some of them down onto my local physical device, and sometimes I slurp them down onto someone else's local physical device, for example, Google's data center, right? And I only use the Google data center because they're the ones that are the nicest at the academics, right? When you grow up, you'll all have to use Amazon, I'm sorry. So one of the things that I slurp down the most often is the Ubuntu operating system. Why is that? Because it's slightly more well-behaved than Alpine, and it's one of the top 3 most popular operating systems for a container. To my knowledge, everything in the universe runs on containers, right? Okay, so I'm slurping down my operating system off of the ether. And when I finish slurping it, I want to make sure I got the correct operating system and not one that's full of security hole, like Swiss cheese, right? Swiss cheese is the thing that has holes in it, right? Your operating system could be that with respect to security paradigms. What are some things that your operating system can do that you might not want it to do? Well, your operating system can do things like read and delete files on your computer. And if you're anything like me, every single program you runs on your computer really, really wants to save your credit card information. Have you all noticed this happens? Like, I really just want to order a pizza on the internet, right? Because I don't want to talk to a human on a phone, right? I don't get paid enough for that, right? So you save your credit card information on your computer so you can order pizzas faster, and then you're like, wait a minute, why does my computer know my credit card information? It doesn't even have a job, right? So what I want is I want my operating system to not be full of Swiss cheese. The way I make sure it's not full of Swiss cheese is I find sources that I trust to get my operating system. But when I get my operating system from those sources, how do I trust that no one fiddles with those bits and bytes while they're flying through the ether on their way to me? The way I do that is I ask the people on the other side of the ether, I say, dear people on the other side of the ether, can you please add up all of the bits and bytes in your operating system and do some nonsense to them? And then I will do the same nonsense to the bits and bytes when I get them through my straw, and I will see that we have the same bits and bytes, and therefore I have the operating system that you have guaranteed to me is secure. Now, you still have to trust someone else to do all of this, right? But now you at least know who you trust, and you don't have to trust intermediaries. You don't have to trust people on the network. The only thing you have to do is trust the person that puts the file up somewhere and hosts, ideally at the same place, a much, much smaller description of whether that file matches some specification or not, right? So it could be the case at very low probability that someone creates an unsafe version of Ubuntu, uploads that somewhere that looks an awful lot like Ubuntu, and I click on the link and download it. That can still happen, but it is no longer the case now that if something happens to the Ubuntu between the website and where it's getting to me, I will not be able to detect that. Right now, I'm able to detect this at very high probability. Every change should change all of the elements of the SHA256 hash. With 256 bytes, that means getting the same hash has a 1 over 256 probability. 1 over 256 is how big of a number? Yes. So 256, right? So each one of those tens, so that's 25 tens. So we have a 75-digit decimal number, no more than that. We have a roughly 78-digit decimal number. A million is 6 digits, right? So we have 70 more than that. Or we can say, for example, let's see, so 256, so that's essentially 2 to the 250 times 1 million. And so mil has the mil prefix because there's a single one of it, and then bil has the bi prefix because there's a billion of it, right? So what we need is something that represents 25 illions, which is probably like duodecipentillion or something? No, it's quintillion, right? Does anyone know how number systems work?
Something like that, though.
Yeah, something like that, though, right? It's a big number. Okay. So there are uses for hash algorithms other than security and other than cryptography, and one of the examples is the hash table and the hash map. Do you all say hash table or hash map? We all say hash map? That's pretty confusing for me. Okay. Well, like map is... I understand maps are just sets of tuples, right? Tuples. They're sets of ordered pairs. But I would like it better if they only referred to the higher order function, right? Now, of course, you can abstract a higher order function as a set of ordered pairs, right? We all understand this. Okay.
Why does table?
Well, I don't know.
There's no collision meaning.
There's no collision what?
With the meaning. Yeah.
There's collision with the semantics. There's a linguistic collision, but not a theoretical collision. Okay, so here's an example of a hash table. Not really. Here's an example of computing a hash. I've expressed these as signed. Do we all know what this is doing here? Let's run this code. You all like running code, right? No, I pressed a button. What did I press? What is happening? I don't know what I did. Everything's breaking. Did I crash my slides? Look at this. Do you see the cursor moving around?
Yeah.
Oh, okay, now I can move it. I'm in insert mode?
How do I exit this?
Escape. Nope, that's not doing it. Here, we're gonna F5. Nope, that doesn't work either. Okay, this is new. I've never seen this particular combination of behaviors before. Have you noticed the hamburger menu's gone? And it's back, right? Where were we? We were here, maybe? Okay. All right, so let's... oh! Okay, I think it's when I copy-pasted something. Oh, my computer's just, like, having a time. Okay. Can I hear it from Microsoft Windows, everyone? I am sure no one here used Linux like 3 years ago, and now you all do it. I'm happy for you. Who used it?
I've been using it since freshman year of college.
Were you here your freshman year of college?
No.
So then that would not count towards my total of people here using Linux, right?
Okay, people here, I guess.
And you've been here for 2.5 or 3 years? Were you using Mint? What were you using? Were you using Arch the whole time? Okay. Do you like it? Okay. I thought it was important to show this, the sign. You can take that off and then your numbers don't line up, which I find pretty obnoxious. What do hashes do? Well, we take, in this case, string data, and we return some value. One of the problems with Python hashes is they're extremely poorly behaved on integers. But I think depending on the integer you give them, you can get them to be really interestingly behaved, pretty interesting. Do they go up to, where does it break? If I add 150 to this, does it keep going? Okay, and then so, there we go. Whatever's going on internally in the Python hash function, something weird happens right around 2 to the 64, which is pretty unsurprising, right, because that's the size of our long type in C. But it's pretty interesting that it's 8 less than 2 to the 64, so what are those extra 8 values being used for? I think there's some like pretty interesting stuff going on with the Python internal integer storage type, where they do things like, they store sign bits, but they also store like overflow bits or something in there. So I'm guessing we're missing 3 values that are storing special characters, but I don't know what they are. What this means is I suspect, and I don't know if this is true, there might be some weird behavior around here. No, the bit links are as expected. Okay, so anyways, we take hashes of things, and we can hash strings like ANC, and we can hash functions like print, and we can hash what's everyone's favorite expression in Python? The lambda expression. Good job. Okay, we can hash a lambda expression. Can we hash hash? Yeah. Yeah. We can hash the function bit length, and we can hash the value of bit length, and they're different values, right? So hashing is fun for the whole family, right? And we use hashing to produce hash maps. But we can also use it to do other stuff that's more exciting. Here is how I think of hashing. And I've been informed by some people that there's, quote, a lot of math on my slides. This is not math, right? This is code, so this is law tech, so it's computer science, right?
This
And
looks an awful lot like the math that I'm doing right now in 251.
I think in 251 it might be math, but in this class it's computer science, right? Do I have any mathematicians in here that can confirm for me this is computer science?
No, this is computer science.
I knew it. I knew. Right? Okay. So let's just think through this theoretically, right? We're going to let M be the size of some hash table. And we want a well-behaved hash table that has nice features, like it being unlikely that when we take some piece of data and we apply a hash function to it that takes that data and turns it into a numerical value, usually positive, that we can use that numerical value as an index into our table, so we can store that data somewhere we can look it up easily, right? Okay. So let's take 2 values then. We're going to take A and W, which are both elements of the naturals. And this is, remember, this is not mathematics, so that naturals contains 0, right? Okay. We take W that is less than the size M, and now we know, because of this comparison, that that whole time this M also should have been a natural number. Now we know it's a natural number because it's the size of something, and the natural numbers are the counting numbers. And that's the way we can tell 0 is a natural number, because it's the size of the empty set. Okay, so we have a W that is less than M, and we have a greatest common denominator. What's the greatest common denominator of, I don't know, 9 and 6?
3.
Okay, good job. What's the greatest, I don't know. What are some fun numbers? What's 17 cubed? You don't have to do that one. I can't do that one quickly either. Well, I mean, we can do it, right? It's 16 cubed plus a bunch of nonsense, right? So we can get there pretty quickly. Okay, so anyways, we want A and W to be co-prime, and I expressed this using GCD, right? Is there an agreed upon way that you generally represent 2 numbers as co-prime other than specifying GCD? You just do this?
Yeah.
This is the only way I've seen to do it, but I hate this because GCD is It's a function. It's not like a property. Becomes a property when you say equals 0, right? But okay. So we take two positive co-prime integers. And then what do we know? Well, we know, therefore, we can take any integer value, any possible integer value, and it can be mapped into the natural numbers modulo this m value. And notice that the natural numbers begin with 0, right? So that's a very important thing to notice. You don't like my syntax? Okay, what's wrong with this?
Why is that mod n?
M should be in parentheses.
If you tell me what to type, I will change the slides. I don't know what the conventions are.
Is M a prime number?
I think it helps.
But not exclusively? Like it's not necessarily a prime number?
So I'm making no guarantees about the behavior of this right now, right? So you would generally speaking select a prime number for performance, or for one kind of performance. You would select a prime number to make it unlikely that you have collisions. Okay, but when I say unlikely to have collisions, now we're already making strong assessments over two things, which is how sparse or how dense this table is, right? And also another form of optimization, which maybe we want to be able to compute the divisions very quickly, right? Because if we're taking a hash as modular arithmetic, that means we're computing a remainder. And we can compute remainders of power 2 much faster. So my impression is that if you want the theoretical niceness in a mathematics class, you would probably use a prime number. In this class, you would probably use a power of 2. And the reason for that comes down to the different usefulness, right? We don't have to write proofs of the goodness of this. What we want is our computers to be fast. We're already using a hash table instead of something with provable bounded time, right? So that's how I was thinking of it. Okay, so what is an example of a hash function? Well, we take our a value, which is co-prime with our w value, and we take our x value, which is the value for which we are trying to find its home within our hash table, right? We take that mod w. Has someone put this in Discord yet? How am I supposed to change this? So it's in brackets? I looked this up somewhere, and that's how it was expressed in like a textbook. Okay, all right, okay, so we take a to the x mod w. The reason I brought that up now is I'm not sure if there's conversions on accepting mod this way. To me, this looks atrocious, because that's...
That whole part should be in parentheses.
Which part?
The mod.
Mod w should be in parentheses. It should be paren mod space capital W and paren.
Yeah.
Just like, okay, like tell me what this is supposed to look like, and I'll change it. Okay. All right, so we take a times x mod w. We divide that by w, and we multiply that by m. Right, so what's happening here? All of these numbers on top are strictly less than w, which means that this value is less than 1, which means that when we multiply it by m, it is less than m. We take floor division so that we get back to an integer. In this case, if this is Python floor division, it's a natural number, and I don't know what it is in mathematics, so I'm going to say it's a natural number. Yes?
Why do we floor it? Like, why wouldn't it be, is it because computers like integers better? Because wouldn't it be more, like, precise and have less chance for collision if you had more, like, decimal numbers?
How are you going to put something in the 1.7th position of an array?
No, so that makes sense.
Yeah. Thank you for your question.
Yeah, thank you.
Yeah. Okay. Not to worry. The much ballyhooed prime has appeared. This is a prime of the form 2 to the n plus 1. There's a name for those primes?
Mersenne.
Those are the Mersenne? Okay, so this is a Mersenne prime. I believe there are 5 of these. Are there 5 Mersenne primes? Does anyone know?
I think there are...
Or 5 known. 5 known.
Yeah, there are infinitely many, probably.
Okay, you can't say there are probably. You can. Okay. So I selected a prime, and the reason I selected a prime is because I want well-behaved mathematical properties, because this is something I've been trying to do for a while, which is I think I have successfully written what probably constitutes a proof in Python using assert. Unfortunately, this is like an extremely weak proof in that this uses exhaustiveness checking, so this is an exponential time proof, which is disgusting, right? So I should feel bad about myself for doing this. And among other things, I imported math just to use the math floor operator, so this looked the same, even though, of course, that's just integer division, right? Okay, so we take h, which has some x value, the value that it's going to compute, and then it has the parameters a, w, and m. That is math floor of a times x mod w divided by w times n, right? Noteworthy, right? This is float division inside a math floor, right? Pretty odd. Okay. I'm going to load up my a, my w, and my m. I'm going to have, what is this? I'm going to have the size of my hash table. That's m, so that is going to be size, what number is that? Okay, so this is 8, and we shift 1 over by 8, so how big is that? How many elements are there in my hash table? Sorry, hash map. You all say hash map. I asked so I could say the term you like, and then I defaulted to hash table.
Is there 257 in the hash map? Oh, now I'm...
There's 257 is a parameter to the hash function. There are 256 entries to the hash map. Right? So I'm creating a table of size 256, right? Let's see, W. Ooh, W is supposed to be smaller. I wonder why I picked a big W. I have my W here, which is OX10, left shifted, a left shift by the size of OX10. How large is this number? That is hexadecimal 10, that is decimal 16, 2 to the 16th. 2 to the 10th is, well, no, we can do it the other way. It's 256 squared, right? Which is roughly 64,000.
65,536.
Spoiler alert? Okay. Which is also the number of unique values in a 16-bit integer or a short. And they're also called wides somewhere. They're wide characters and short integers. Okay, right. So what do we do here? I do an assertion statement. I assert that all things that are not coprime, and then I hash everything in the possible range. And I say, look, they're not equal to each other, blah, blah, blah. Okay. This runs a little bit slowly, because I'm asserting everything within the range of the hash table. But you can do hash table computations. And what are some other values we can put in here? I did data. We can do this too. What's another data? Yeah, there you go. So these things are all interesting. What am I intending to show you here? I am intending to show you that there are different hash functions with a variety of different behaviors. We can change different parameters of a hash function and get different results. If you're working with hash tables, you should think about optimizing for collision. You can throw all of this in the good programming language, but you don't have to. We talked about different W previously because I got an extremely leading question that I did not coach the witness to ask that question, right? So we can take different W values, for example, but we can also take them to be a very precise value, which is we can take a W value that is the same size as the C language word size, which is also the same size as the Python language word size, because C and Python have the same size words, right? Because Python's written in C. When we do this, we get to use shift operations in our hash table, which are much easier to work with, as we will find out when I make you all write your own division, right? Dividing by powers of 2 is considerably easier in computing than it is to divide by any other number, which means that this is a gazillion times faster, approximately. So, look out for this. How many of you all are super familiar with bitwise operations because of the macros homework? Well, I can't believe every single person in here raised their hand. That's incredible. Some people are raising their hands twice, and some people are like pretending they're somewhere else, and those are the exact 2 appropriate responses to that. Okay. What is a collision? A collision is the bad thing. The collision is what happens when the person making the malware manages to get the same digital signature as the person making the operating system I want to use. That's bad. That's the bad outcome. That's when you can lie, cheat, and steal. And a collision occurs when there exists two values, which we're going to call x and x prime. One of those is an operating system. One of those is the season of Game of Thrones that I downloaded that destroyed my computer. We note that the good operating system and the bad season of Game of Thrones, which is seasons 3 through 7, have different binary representation within a machine. We do not care what the binary representation within the machine is. We simply note that they are different. Yet, the hash of these two values could be the same. I heard someone ask for an example. Not to worry. Is this the thing that has... So it is quite possible to find two distinct values for which the hash value is the same. It is much easier with hashes that are not intended for security usage, like Python hash, which means that if X is the malware and 7 is the operating system, I have a problem because I check to see that the hashes are the same, to see that I have the thing I want, and that the two values hash to the same signature. So collisions are bad. This is the no hash collision assertion, right? We have X sub 0, X sub 1, and you have to assert this for all values X that you're going to possibly use. For the sake of computers on the internet, right, this is a large number of hash values. This is every file you could possibly download, including the HTML pages and so on, right? So that could be a lot of different things. We have different goals depending on what we're doing. In a hash map, you are intending to minimize collisions, but you have other performance considerations because things like linear probing, cuckoo probing, what are the various hash map algorithms you've seen, right? Any perfect hashing? Okay. So there's a variety of ways to manage collisions in your hash tables, and you minimize them, but you do not have to eliminate them to store values in a hash table. Now, for cryptographic reasons, we do want to absolutely avoid collisions, and the way we do this is by making the probability of collisions very small, 1 over 2 to the 256. It makes them as minimal as is information theoretically possible within finite memory. Does that make sense? Right, so without infinite-sized hashes, we couldn't do this. Do you all know what the codomain is?
Yeah.
I know you know. Okay. So I'm holding a function. What's this function? It's the Python hash function. It seems to hash things into the range 2 to the 64 minus 8, positive or negative. I don't know if that's true. If you're looking for something to do, simply start hashing random values and see if you can get a number higher than that. I suspect you can't. I don't know for sure. And it could also be implementation dependent. So some of you are using Linux. Can I hear it for Linux? Do any of you actually like Linux, or do you just do it to be like that? Okay. Yeah, I respect someone that can tell the truth, right? I used Linux for a while, and I was like, why am I doing this? And then I switched back to Windows, and then I could attend meetings, and then I got paid to go to grad school. So there's reasons to use Windows. That's why I use it, right? Okay. So if we have a function, such as the hash function, it takes some values, and it has a set of destination, which is the set of all possible values that the function can take on after it has been applied to some argument, right? And so we call this the set of destination. This is the codomain. In the case of SHA256, it is important to know what the codomain is because you're going to be fiddling around with bits and you want to get the right number of bits. All that we are doing with SHA256 is we are taking a bunch of bits and we're scrambling them around as one would perhaps hash browns or hashed. What's hash? Hash is hashed something, right?
Potato.
Potato?
Yeah.
Well, yeah, so you can hash browns, but you can hash something else too, right? Like what's corned beef and hash? Is that potate?
That's also frequently potato.
That's also potate.
Yeah.
Can I hear it for potatoes? Y'all having a good time today? I didn't sleep enough last night. That's why I'm like this. I had a very good time trying to implement my own computational linguistics library in Python, which is a problem because I don't know computational linguistics, so it didn't work very well. Okay, here we go. Here's another test. We can assert that there is not hash collisions here for x in range m. Okay, we're going to run this. Then we're going to talk through it line by line. Okay, you've already seen the hash function. I expressed it with a lambda. Why? Because lambdas are better. Why are they better? Because I said so, right? Do all of you still use def keywords in Python?
No.
Why are lambdas better? Yes.
Because I like them better.
Why do you like them better?
Because I don't like pressing enter. So the thing that actually got me into lambda was doing these things all the time. And so I started inlining a bunch of lambda operations. And when I started doing that, it's really annoying to put new lines into these scripts, right? So because I use Python primarily as a scripting language, I started using lambdas really extensively, if you must know. Okay, so AWM, right? We have a table size. We have some W size. We love W's. This is a prime number, I hear. I didn't check. And what do we assert? We assert that if we apply the h value to all x for x in range m, we get back precisely the same set of values, right? And I know I was sorry that I had to apply set to range to do this in Python, but I don't know, that's pretty good. It's pretty cool we can write this in a programming language, right? So what this means is that when I iterate over x up to 255, because this m is 256, so we stop before that, so 0 to 255. Why? Because 0 is a natural number, right? I feel like you're not even complaining about me saying 0 is a natural number anymore. That's taking the fun out of it. Okay.
0 isn't.
Sorry?
0 isn't that.
Okay. Are you an algebraist?
I am whatever class I'm in.
You're a traitor. Okay. And so this hash function will take on every possible different value within that set, but it will not take them on in any particular pattern or order, which we can see do we need to do the whole thing? We'll just do the whole thing. Did I define m? No. What'd I do? Oh, yeah, double in. What? What are the a, x, and w? Wait, hold on. I have them somewhere. Define. Okay. Please copy. Ah! Did that work? Okay. It's x, a, w, m. Does that seem right? Math is not defined. That's true. Math defies definition. Here we do. We have all of them. There you go. Good job. Okay. The way to visualize this, or the way I am recommending you visualize this is 200 to 256, right? That's the number we had a hard time naming. I think it's by deciquintillion. I don't know. What do you think it is? I feel like it's fine to say I'm wrong, but you should have an alternative. Vigin quintillion? Is that legit?
Sounds like someone named Vigin wanted a number.
That's no cap? All right. I love saying no cap. That's my favorite part of being a professor. Like, if I had a real job, do you think I could say no cap at work? No, everyone would get super annoyed with me. But here, if you get super annoyed with me, you can't do anything about it. Okay, so we have, these are called bins. You can also call them buckets. You can also call them ranges. What did you say? Quatravigin?
Well, it's Q-U-A-T-T-U-O-R.
Quattro.
Cool. All right, so we hash some values, and they go in different bins. For example, if we hash x sub 1, it goes in bin 2, x sub 3 goes into bin 0, and then x sub 2 goes into bin 2 to the 256 minus 1. This is what SHA256 is doing. It is taking inputs. It is finding which of these bins they go into. It is very unlikely it goes into the same bin as something else. It is maximally unlikely as possible given finite storage limitations, right? So there is not a guarantee that there is never any collisions, but 1 divided by 2 to the 256 is a very small number. How small, you ask? That's a great question. That's pretty small. That's like 1 over a quadrillion. Okay. Okay. So does that introduce hashes? Do you feel like you understand hashes worse than you did when I started talking? Yeah.
That's a question. Yeah. So, do you, in industry, when this is implemented, do they still implement collision checkers?
Yes.
Or are they just like, nah, okay.
Yeah. So different people probably have different opinions on this. In my view, the Hadoop distributed file system is the most advanced hash table in existence, hash map in existence. And it does all kinds of things to assure there is absolutely never any collisions, right? There is, I think, literal 0% probability of collisions in that. And they make really strong assessments about things like there won't be a collision if I start writing to a hard drive while that hard drive fails and stuff like that. The Hadoop distributed file system has the uncommon misfortune of being written in Java, so we'll never know how it works. But it works really, really well. So, okay, what's coming up is a trick question, so get ready for the trick question. Are you all ready? There's a forthcoming trick question. Okay, so be ready for that. Okay, so we're going to start with SHA2. The 2 stands for the fact that there's 2 of these. You can tell it's made by mathematicians because 2 is the second one and there was not an SHA0, because 0, as we all know, is not a natural number, right? And it is not, in fact, one hashing function. SHA256, along with 512, are both quite common. SHA256 is of academic interest to this class because it is one of the 2 cryptographic functions, we'll say, that became the foundation of Bitcoin, which is our sort of motivating example of the piece of software we're building towards, right? And it was put together by NSA. Can I hear it for the NSA? Nope, that was the test. It's the United States federal government. Okay. Can I hear it for the United States National Institute of Standards and Technology? Yeah, they're okay, right? Yeah. It's okay. So I got an email today from like someone who works for the university. It's like, hey, do you want to come to a training with the Department of Homeland Security? I was like, is this a trap? That was what I thought, right? And you don't have to think that, but that's what I think. Okay. SHA1 was released in 1995. I don't know anything about it. It's insecure. The way it was secure is it was a little bit too easy to cause collisions. There was some predictable way to generate collisions. If there exists such a way to generate collisions predictably with SHA2, it has not been discovered yet. If it hasn't been discovered yet, does it exist? Probably not on existing hardware, right? You would probably have to develop some other kind of computer to find the problem. Now, we thought that same thing about RSA, and it turns out there were assumptions we were making about our computers that were incorrect, like that it doesn't matter how many nanoseconds it takes to find a hash. Versus RSA, which is the next hashing, or it's not a hashing, the next cryptographic algorithm. SHA always takes the same amount of time to hash something of the same size. That's pretty cool. This is slightly better. So SHA2 is regarded as secure in 2025. Versus other algorithms, it is also considered to be secure at both of the block sizes, so 256 and 512 are both considered secure. Many of the existing algorithms we've been asked to push up are bit size, and that will be the subject of the homework after. SHA256, I'm going to make you implement 496-bit integers. And that's decimal 496 bits, right? And 496 in decimal is how much in hexadecimal? It sounds like you're speaking decimal, which feels like that's cheating.
No, was just saying, you were saying 496.
I was saying 496. I meant to say 4,096. What I meant to say is 2 to the 12th. Sorry, 2 to the b. No, I was close. This much, that much. Okay. You need that many bits. Okay. I have been unable to care about sizes other than 256 and 512. I understand they have usefulness. Everything else I'm going to say is essentially only going to be about 256 and 512. The other ones use 256, 512, and they start late or stop early or something, so they're all pretty much related. If you understand either 256 or 512, you will understand all of the other ones. Okay. What is this used for? With RSA, which is the subject of the next segment after SHA, they're used for digital signatures. By themselves, they're used for certificate validation. So if I give someone some amount of information, I compute the SHA256 hash over that information. I provide that SHA256 hash, and someone who knows the SHA256 algorithm can take my information, compute the hash, and verify that the hashes are the same. And so it is also used for file integrity verification. To me, it is half of, well, is that true? It is half of the facilitating technologies for blockchain. There was one other form of insight that was required beyond the actual cryptographic algorithms existing. So it is not half of Bitcoin, but it is half of the requirements for Bitcoin, is how I would describe this. Okay. We now all have to say something. So in general, compared to how much of a chaos goblin I am, many people that teach cryptography care about things like professionalism and responsibility. And so one of the things that I'm required to do is tell you that you are not allowed to actually use cryptographic algorithms you write in this class. And the reason for that is that most of these things are insecure for reasons that are very difficult to explain in one semester. And so even if we correctly implement SHA2 compared to the command line arguments, there could be features of our code that are non-obvious to it that cause it to be insecure. So even though we will implement cryptography, we are going to assume it's insecurity because we don't know what side channel attacks are. Who knows what side channel attacks are? Yeah, they're confusing. Okay, so please raise your favorite hand and repeat after me. Okay. I will not use SHA256 that I write for security critical applications.
I will not use SHA256 that I write for security critical operations.
Thank you. What is a security critical application? If you care if it's secure, you cannot use code you write. Okay? And if you don't care, you also can't use code you write because someone else might care. Okay. SHA256 has a 256-bit output length. The sizes on this are so confusing because there's like internal block sizes and chunks and stuff. So anyways, what we're doing is we're taking any bit string of arbitrary size. Is that true? No, but most things are smaller than 17 million terabytes, right? And technically the standard doesn't apply to file sizes bigger than 17 million terabytes, but in practice you can just keep hashing them and it's more or less fine, right? So SHA256 is not like generally accepted as secure above this size, but there's also no competing standards. So essentially you can use it for any file of arbitrary size, any data set of arbitrary size, any piece of information of arbitrary size, any combination of pieces of information of arbitrary size. And it will always give you back something that is of size 256 bits. Okay. How's it going to do this? I'm glad you asked. Are you all warmed up? Clear your minds. Focus. It requires holding a large amount of information in your brain simultaneously, even though no individual components are actually particularly challenging. So it's a very novel algorithm in that sense, where each component is simple and the aggregate is not. Okay, there are two stages, pre-processing and hash computation. More of the work is in hash computation. So pre-processing begins by initializing a 256-bit, so it's the state variable This is sort of the working variable. You could argue this is just one variable of size 256 bits. Often it is represented as 8 values of size 32, because 8 times 32 is 256. You can compute these values fairly easily. They are what it says there, fractional parts of the square roots of the first primes. What's the first prime? 2. What's the square root of 2? 1.414. How do we turn that into a fractional component? Well, we take this value, and we're going to need a 32-bit representation of the fractional component. So we do 2 to the 32. And so we take the... no, we should do one other thing first. Hold on. We're going to subtract 1 from this to have only the fractional component. Okay? So the fractional component of the square root of the first prime, that is going to be expressed in bits somehow. The way we express that in bits is by multiplying it by some large number to get it sort of out of the space of being smaller than 1. And then we're going to take the binary or hex representation of that. I think this is going to work. I don't remember if it does. Ooh. Int. What am I doing? Does anyone know what I'm doing? 6A09E667, 6A09E667, okay. Is that right? That one looks wrong for some reason. Oh, BB67AE85. Okay, what's the next prime? Is it 5? And this one we have to subtract 2 from, right? 3C6EF72, okay. Because we only want the fractional component. Let's see what happens when you leave the 2 in. It just has leading digits, that's all. But you can also take this, and that still works as well. All you have to do is you have to get the portion of the square root that is in between 0 and 1. So it is the square root mod 1. Perhaps I can actually do a mod 1 here. Does anyone know how modulo works? Open to suggestions. By the way, I tried to write this in C and I just gave up. It was too hard. Okay, so 5 is prime. Why? Because what's the prime factors of 5? 5. Easy, right? We take that to the square root and we get... I actually have no idea what the square root of 5 is, and I don't want to compute it. 2.236, right? So we take that %1. We multiply that by 2 to the 32. Which we can't do because it's a float, right? So we multiply it instead. We get this value. This value is not of particular interest to us. So we cast it back to an integer. And I don't think that's actually called a cast in Python, right? It was interesting to me that this seems to truncate, not round. I was surprised by that. I was surprised it did that in the hashing standard. I assumed they would round. And so I was surprised this was a 2 instead of a 3. I expected that to be a 3. Okay, so you can compute these. Okay, all right. Restore our minds to our objective. We are holding in our thoughts an operating system. That operating system is not necessarily a multiple of 512 bits in size. So we have a problem because we are going to break this up into an array of size of 512 bits and process each one separately and sequentially. So in order to deal with this, we are going to figure out how long sum m is. We are familiar with the notion of figuring out how long things are because we've used the bit length, whatever it is. And I think I can't do bit length of this because it's a string, right? But we can say and we can see the bit length of various values, right? Okay. So we're going to do this thing where we pad out the array size, right? So in hash tables, you have often initialized a hash table, perhaps in NumPy, to be an array of some fixed size, and it doesn't yet contain information. We're going to do that same thing here. We're going to take a file, we're going to copy it into an array, and when we copy it into the array, it might not fill out the array to some multiple of 512 bits. And the way we're going to address this is we're going to add some bits to the end. What are we going to add? Well, we're going to figure out how many bits long our message is, and then we are going to find the smallest non-negative number because we are going to add some bits onto this. We have to add something onto the end that tells us how many bits we have, and also the special value here, 65. So we're going to take something that is L bits long. We're going to need to store 65 bits worth of information. And so we're going to need to find how many bits we have left over to get to be a multiple of 512. Oh, this is the way you wanted it to be expressed, Indy, right? The parens around mod?
I think the other way, since it's like not says equivalence, the other way was fine. But that should be like congruence, not equals.
And congruence is 3? Okay. Is someone writing all this down?
Yeah,
Okay, thank you. Okay, so this is how long my file is. Oh, is that a hand? Are you asking a question?
Yeah. What's up with 65?
We'll get there, but thinking back, we put a cap on how big this thing was that was of size 2 to the 64. So we can store sizes up to the maximum size of this in those 65 bits. So these 65 bits are reserved to say how large the payload is.
Okay.
And we haven't done that yet, but there's a reason that's a power of 2 plus 1. Okay, we have something of size L. We're going to find a value k, which solves this equation with congruence, which is triple equals. Or, well, I shouldn't say triple equals either, because that's a different operation. Okay, so we're going to take our message m. This is essentially where you would start writing code when you're working on the assignment. Okay, so we're going to take our message m. Someone has, clickety-clackety typed something into us. We're reading a file out of the file system. We're curling something off of the internet. Somehow there's some bits and bytes we want to pass around, right? And so we're going to look at those bits and bytes, and we're going to say, how many bits and bytes do I have? And we're going to say, oh, we have roughly 513. You're like, oh, that's a ludicrously obnoxious number, right? So in order to get up to the next 512, I know I'm going to need to add 65 to that 513, which brings me to 578. And then I'm going to need k to be the remaining value to get up to the next multiple of 512. So I need 512 times 2 is 1024 minus 513 plus 65, which is, I'm not going to do more mental math in front of you, but like whatever that number is, and it's roughly 460 or something, right? Okay. These bits are going to be a single or a solitary or an individual 1. They're then going to be k zeros, so I'm going to terminate my file with a single 1, and I'm going to follow that with a large number of zeros, and this number of zeros is going to be probably an even number of zeros, because I'm going to save 65 left, and I took 1 away from something, and I'm probably storing things that are multiples of 8 in size, right? So it's probably going to be a multiple of 8 plus 6 number of zeros, okay? So there's going to be a 1, there's going to be k zeros, k is the value that satisfies my modular equality, and then I am going to take the length and I'm going to represent it as a 64-bit integer with leading zeros, and so I have 1 plus n, or plus k, plus 64 bits. Do you have a question? That should say k, yep. Cassie, do you have a question?
I had the exact same.
Yep. Yeah, I believe this should be k. You know, I posted these slides a long time ago, and I asked for people to look at them. So, haters can't be choosers, right? Yeah.
It seemed equally plausible that there was a value I had either forgotten or you had forgotten to define called n that was important in a subtly different way.
I have never once forgotten to define a value. How dare you?
Never.
Never.
I apologize.
Yes, that's highly offensive to members of the value remembering community. Here's some Python. So in Python, we have a message. I often think of messages as strings. Why do I think of them as strings? Well, oftentimes the thing we're passing around is JSON in practice, and JSON is string representable, right? So I often think of these as strings, even though there's nothing compelling them to be strings. The other thing that I think we pass around is binaries. Well, you can open a binary file in a text editor and look at it. It's just UGO, right? And you can also open it in a hex viewer, and then it's also UGO, right? So I usually demonstrate this with strings, right? Interesting that there's some spaces at the end of this, right? That matters. Hello there, I am a message, period, space, space is a different expression than hello there, I am a message with no spaces. So I'm going to take this thing and I'm going to multiply it by 15. I wonder why I'm going to do that. That's probably going to be some fixed length. Okay. No! Okay. So here's M. And the reason there's two spaces there is because I learned to type in 1997, and there was a very short period of time where people were taught to put two spaces at the end of their sentences while they were typing. I don't know why that is, right? But I have not been able to kick the habit. Okay. We're going to have some x value that is 1. Who knows what that's representing? I often use variables, and I don't know what value they represent because I haven't introduced them previously, and I don't know what they stand for. That one goes out to all the homies. Okay, so what are we going to do now? We are going to encode this message as a Unicode string. I don't use encode in Python very often. I have to do so for the sake of this example so I can compute the bit length, okay? So this is the UTF-8 encoding. You see it just has this B in front of it. I thought that B stood for bit string. I don't know if that's correct. Does anyone use Unicode or encode in Python and know how it works? Noticeably, it's the same. One of the ways to probably see what's going on here is we take another string, and perhaps we put a new line in it. Oop. And perhaps if we encode this, we'll get some interesting features. Encode UTF-8. Nope, not 9. And so in this representation, we see we get the representation of the non-printing characters, right? So perhaps that is of interest to us. Okay. Now with like an elaborate wizard, or perhaps even a magician, which I think is actually less powerful than wizards, I'm going to reveal why I needed x, which is equal to 1. I needed the smallest possible numerical value, and I didn't trust 0. So I'm going to compute the bit length of x. Length. And I'm going to see, oh, it's size 1. Okay, and so I'm going to compute the length here by, what am I doing? Okay. How is that 453? Wait, why is x? This seems wrong. All right, well, let's keep going and see what happens. Okay. Okay. We can compute our k value by taking our L value, which is the length of our bit string. I'm sure this is supposed to be 8. I'm going to say this is supposed to be 8. Right, surely this is how many bits it is, right? Does that seem better? How many bits does that look like to us? It's 435 ASCII characters, 8 bits each, right? So it should be that much. Okay. I think I was trying to get the bit length of a character here, and I didn't know how to do it. That's what I'm going to say happens. Okay. And so we're going to compute our L value. I think this is wrong. If someone can figure out how to get the bit length of an well, I mean, it says UTF-8, right? So maybe we can just assume 8. If there's a built-in Python way to express how many bits a character takes up, I don't know what it is, and I would like someone to find it if they can.
We have 20 minutes left and we're halfway through the slides. Can we record this?
Yeah, that's okay. I mean, we're on pace. So, and I think you will find this matters and you want to think about this. When we take some string, we compute its length, we convert its length to bits, we take that essentially, not quite, modulo 512. Really what we do is we take that plus 65 modulo 512. Because we have to have those 66 bits left, we take this value, which is modulo 512, and we subtract it from 512. Oh, and this is going to give us the k value. So we can then pad our input string with 39 bits of zeros. And then we can also include the length of the message, also represented numerically in binary, in bits, using up to 65 of those bits. So we're going to take a message, we're going to prepend a 1 to the end of it. The way we're going to prepend a 1 is we're going to take a 1 and we're going to shift it over by 8. We're going to shift it over by 7, aren't we? Yes, because 1 is already shifted over by 1. So we're going to add a 1 to the end of our string. We're going to have some large number of zeros, and then we're going to have the binary value representing the size length. And I'm sorry my L's and 1s look the same. Okay. This is going to be a really nice simplifying assumption for us because the next thing we have to do is split our input into 512-bit blocks. Everything has to be worked on in exactly 512 bits, and you have to know what all 512 bits are at every point in time. This was a bit novel, and I did not expect this. It seems to be common when I've looked at different specifications of the algorithm, and it is specified in more than one place, so not everyone does this. But it seems more common to one index the blocks. So we say we have n blocks, and the final block is block n. It is not block n minus 1. I expect when you are working on this, you are going to write very, very short strings, and so therefore you're probably going to get everything working before you do multiple iterative blocks. I definitely got my code working single block and then got it up to multi-block after that. Depending on your process, you might just extend to multi-block and find everything works, and that did happen to me. I hope that happens to you. Whatever file we have, we break it into chunks. The last chunk is not necessarily of size 512. It can be the case that you do not get up to a 512-byte barrier, but the 65 bits you have to use to store the size of the file puts you over the barrier. That was a complicated edge case. It was very annoying to implement. So look out for that as well. Okay. This is the type of the hashing operation as best as I can express it. We have a function that takes some message, which is 512 bits, and it also takes some initial value. These values were initialized to the fractional components of the first 8 primes, which I showed you how to compute, and I will provide for you as defines. There are 256 such bits, usually represented as 8 32-bit integers, and this is going to produce some new h value, h prime, which is also a 256-bit, or a bit string of length 256. So what we're doing is we're updating our h over time. The importance of noting we're updating our h over time is we are iteratively changing h for each 512-byte block of input, 512-bit block of input. So if we have a previous block's hash value, we calculate the new block's hash value by taking the message chunk, I, and the previous hash value, h of I minus 1, and we do this for each n value. Everything here is one indexed. And that was pretty weird for me. One of the reasons to argue that this is easily one indexed, and this it perhaps makes sense to you, I provided you constants for h superscript 0. That one is 0 indexed, and that's because we start with hash of m1, which means 1 minus 1 is 0, so the h0 constants I provided you, those are sort of 0 indexed, right? Our message chunks are not 0 indexed. Okay. On the macros assignment, I provided some like low-grade direction. This is not necessarily that binding. You should predominantly work over things of size 32. The way I think of that is that there are different instructions in computer architecture. This is a pointer to the sort of advanced optional talk. When you rotate bits in a computer, there is a different rotate value if you're rotating 8, 16, 32, 64, or potentially more bits, and there are also different rotate operators, some of which rotate, for example, 17 bits at a time, including the sign bit or the carry bit, right? You have all written a rotate. If you passed the autograder test, your rotate is compliant with what I expect to work on SHA256. Just be aware of that. So if things look weird, make sure your rotate is still compliant and you didn't change it or something. Okay. And I'm recommending handling all of this stuff with standard int. Okay. We have a series of operations. None of them are too bad. Most of them, you know what they are. You've implemented most of these already. Okay, so how are we going to use this? We're going to take bitwise logical operators, and I think of them as, do we say ternary or ternary? It's ternary? Is that how you say it? Okay. They take all different numbers of arguments, which was quite confusing to me. I'm not super used to working with ternary operators that return something. They are present here, and of course these are choice and median, which we wrote already. Various places on the assignment I have recommended for use. You use U, V, and W because they are common in the literature. You don't have to use these, right? But this is W for word and then 2 previous values with the assumption that X and Y are taken for other values, right? So when you say U, V, and W, those are referring to 32-bit words, which I think of as a uint 32T, and we take 1, 2, or 3 of those in our operations, right? The shift and rotate operations are of different type, because they take a U, V, or W, which is a value in 0 to 2 to the 32 minus 1, but they also take a value in 0 to 32 minus 1. And I call these N, and I use lowercase for that, right? I think you can, in fact, shift something by 1 billion. It's just like not good practice to do that because it's hard to keep track of it. Always use sort of a shift value or a rotate value of smaller than the size of the unsigned integer you're working with. So if we're working with 32-bit values, we use a shift value smaller than 32, okay? There's only one unary bitwise operator, and it's not, bitwise not. This is bitwise not in Python. I think it's not too exciting. We'll take 17. Wait, that's not Python. Oh, is that C? Is there bitwise not in Python? Is that right? Oh, it's negative. I don't know what negative means on binaries here, right? I don't know how Python works. Use C. Okay. This is actually an extremely good example of why I have to teach this class in C. I think it is harder to figure out what Python is doing here than it is to just learn a new programming language. I could be wrong. I think you're essentially learning a new programming language anyways. So this is bitwise not in C. And what bitwise not does is it does the same thing as all the other bitwise operators. You've seen bitwise and, you've seen bitwise or, you've seen bitwise XOR. You know what those do. This is not. Okay. We have the binary bitwise operations, which you've already seen, and, or, and XOR. I give them all to you here. I usually try and specify, just for like something like this, I do specify inclusive or. Little bit too confusing for me to have 2 different ORs floating around, so I do specify inclusive. You don't have to do that. And of course, you can just use single and, right? Note this is single. Single bar, or whatever that is, right? And then caret. In defense, once again, of the C programming language for working with bits, the bitwise operators are more privileged than the Boolean operators where we have to use doubles of each of these, right? So its default language is working in binary rather than Booleans. Okay. You can expose C shenanigans in Python. using C types, which doesn't work in every Python installation. It probably works in mine. And here, I'll just show you what this looks like. It's pretty uninteresting. And I get back C types inside Python. If you need to mess with this in Python, this is my way. I recommend you do it. Pretty annoying that this defaults to unsigned long when I specifically specify I want C unsigned integers. That's one of the artifacts of working in a 64-bit operating system. This is, once again, a concerted defense of the C programming language versus Python. It is very difficult to specify 32 versus 64-bit integers in Python, which means it is very difficult to work with SHA256 in Python because you have to be working with 32-bit words. So there you have it. The purpose of this slide is to introduce that addition is very, very close to being a binary bitwise operation. We can think of it as in the family of bitwise operations. It is a combination of XORs, ANDs, and shifts. So we're also going to be using addition. Okay. We have an extremely nice convenience here, and the encoding lecture sort of set us up for success with this. All of the operations over our uint 32t's and C are already implicitly modulo 2 to the 32, which is exactly what they want them to be respective to. So we don't have to, for example, after every operation, take the modulo value. That is happening built in. That is happening as an emergent property of the electrical engineering implementation of the language. It is extremely convenient for us. This means that C is faster and more precise than Python for this specific application. Yes, it is slower for some things. It is faster for this application. So here's an example of what happens. This is very similar to the code I showed you in the encoding lecture, so I'm not running it for that reason. Okay. We can get the same values, blah, blah, blah. Okay. You are familiar with choice and median. You are more familiar with choice and median than I am because I wrote mine several weeks ago and you wrote yours a week ago. There are various ways to specify this. This median is actually an under-optimized median. This is optimized for human readability. Some of you realized you don't need this many binary bitwise operations in order to achieve median. Good for you. Did anyone use a more compact form for this? I think you can get rid of one or two of these operations.
Wait, but... Well, I thought mine didn't work for the XORs. I thought it was just normal ones.
If this is wrong, it's wrong. Like, these should be inclusive ORs?
Yeah, because if it was XORs, you would have to require there be exactly two of them that are one, not all three.
Here's the answer key. Ta-da! Where is it? Oh no, that's definitely XOR, and that definitely worked. Also, you can look at this as much as you want. It will not help you at all, is what I found.
Yeah, XOR.
I'm like 100% sure it should be XOR, but I don't know why.
There are ways you can do it using OR as well. Just switching around
I had the
logical
same thing, but with
sequences.
regular OR. It worked.
Yeah, the same thing.
Yeah.
Yeah, maybe it doesn't matter.
I feel like I tested it with XOR and it didn't work. Maybe let me try it.
So yeah, so let's the assignments like due or whatever pretty soon. So if we find some interesting corner cases, start sharing your median implementation, right? I wrote 2 of them and I didn't save either one, and they were different. One of them used knots. I don't remember what I used them for. So anyways, choice and median. We tested choice and median. It would be extremely humiliating for me if the answer key is wrong again. But in fairness to me, I tried to write it in assembly, which I am familiar with, and then it didn't run on everyone's Apple computers. And that's not my fault. I couldn't test it on an Apple computer. I didn't know how to do that. Okay. Shifts and rotates are different, and they are different because they have a different function type. They still accept one 32-bit word, but they accept one other thing, which is different. It's actually a 5-bit word, which isn't like a real thing that exists, right? This is how I think of the shifts and rotates. I think you know as much about shifts and rotates as I do. There's a variety of ways to express these. This is rotate right. That's shift right. All we do is we throw some zeros in front of something and we clip off a bunch of bits that we have to. With rotate, we just take the bits we clip off and we put them at the beginning. You've written a rotate. This is 86 rural. which is one of the several, there's a bunch of rotates. And then this is shift right. The L's here are referring to the assembly language long, which is the 32-bit long. Okay. I recommend writing the following helper functions. These are usually called, they're all sigmas. We have big sigmas and little sigmas, and they're underscored 0 and 1. We combine rotates for big sigmas, and we combine two rotates with a shift using XOR for the little sigma. You are under no obligation to write these. I use them prolifically. I thought it was a little bit easier. I've looked back at my code. I don't know that I even saved time by writing all of these, right? So it's up to you if you use something like this. I am going to use it on the slides. One of the very good reasons to use it on the slides is that it takes up much less space. You can use either a macro or a helper. How is the hall so loud? Okay. Okay. So we're going to take 4 steps for each 512-bit chunk. The first chunk is going to be populated with the starting hash values superscript 0, which are computed from the fractional parts of the primes, right? I provide these to you as a define. These are defined initial values. Like, you don't have to compute them live. Think of them similarly to, for example, the inverted ciphers, right? These can be computed offline or they can be computed live. You only use them once because every successive chunk after that uses the hash value that comes out of the previous chunk, right? So we're only using this initial value for the very first 512 bits we look at. There are going to be shared pre-computed k values. These are the fractional components of the cube roots of the first 64 primes. I am also providing these to you. They are computed the same way. Okay? We're going to pre-process. We're going to set a message schedule array. So we're going to populate a large array. I think it is 64 by 32, right? 64-word array. We are going to set the working variables. Working variables are used for each step we take through the 64-word schedule array. So we're going to be progressing through this array, updating values as we go, and we're going to use 8 different words and maintain them as our internal state. We're going to do a series of word-level operations, and then we're going to update the hash value. And I think this is, you just have to write this code. Okay, so we take, what is this? This is from the ith chunk of 512 size, and this is the jth word of that chunk. So this is one of the 32 word values of the 512 byte chunk, okay? Or bit chunk. And it's so hard to say bit and byte separately. I'm sorry if I keep conflating those. So we're going to take these words, which are very short. Chunks are tweets, words are words, basically. Messages can be whatever you want. And we're going to populate the beginning of the message schedule array with those, what is this? That is 16 by 32 words, so that is 512 bytes, right? Wait, 16 by 32? Yes, 256 bytes. And then we are going to progress along the array. And how are we going to do this? We are going to apply sigma to a prior word. And this prior word is different for each point in the message schedule array of length 64. We have 64 words, and we're updating them over time. So we apply the sigma value to a previous word. We just add the previous word. We apply a different sigma function to a different previous word. And notice these are off by 15 and 16. That is why we have to populate the initial values. 16 is the starting index, so we can subtract 16 from that and get 0. So we're going to add up 4 different operations over these, and we're going to populate all of the 64 word entries of our, quote, message schedule array. So you have 64 by 32 bits. Then once that message schedule array is set, we load the hash value into usually what is denoted as A through H. That's a little bit confusing because we double use H. I can't do anything about that. It's the 8th letter of the alphabet. Okay? So I have 64 words, each of size 32 bits, and then I'm taking the different hash values. I keep thinking class is almost over because they're leaving, but I have 5 minutes, which is how many minutes I want. Okay. We have our message schedule array. It is, I like sort of visualize it as in a location. So I visualize it over here, and it is 0 through 63 indexed, 32 bits each. Then over here, I'm holding 8 different variables, and I'm sort of juggling them. I'm going to start at the first position in the message schedule array, and I'm going to perform these operations over the message schedule array, which is relevant specifically with W sub j, right? we're going to take one word out of the message schedule array, and then we're going to take all of these other values and we're going to update them. The way that I think of this is essentially I take these 8 values, which start with the initial hash value, and I sort of shift them over by 1, and then I add some things into them. So the only things that are not shifted over by 1 is D has a special temporary value added to it, which is defined as so. And then because I shift over A, there's nothing there for the new A, so I add the 2 special temporary values together, and these temporary values are computed with the big sigmas, and the choice and majority or median operators, right? Okay, so I have my 8 bits, I'm juggling them, I sort of shift them all over, and some of them I add some values to. One thing that made this easier for me to think about, H falls off the end of the array here, it goes off the end, it gets thrown into T1, it gets added to a bunch of other values, and then that T1 comes back into the starting value. So essentially I'm taking bits, I'm jiggling them up at positions 0 and 5, and then I'm taking those bits and putting them back at the beginning. And I do this the whole time I progress through my schedule array of 64. So I'm juggling my variables over here, and I'm slowly progressing through my message schedule array that I created. Essentially only 2 steps, right? You populate the schedule array, then you run a for loop 64 times doing this operation. Inside the for loop you assign 8 variables each time you update. Set up the array, juggle the variables. Then you're done. That's it. What you get out of there is the hash value. The hash value is what these temporary variables were. So as soon as I finish juggling them, as soon as I go off the end of my message schedule array, whatever values I have there are the new hash value. And if I'm out of message chunks, and like I ran out of slides there, if I'm out of message chunks, that means that's my final hash value. I implemented mine using this. I did not understand that until I worked through these slides. You have worked through these slides, you're probably fine to go to the JS demo. I used the JS demo to check my work, and I used the Wikipedia pseudocode. I copy-pasted into a file, and I translated into C. That got everything to work except endianness, and we'll be working on endianness in this class on Thursday. I think you can do SHA256 now. Look at this if you're looking for something to do. Here's the message schedule array, or well, this is the message schedule array. These are the incoming hash values. These are the values we're going to juggle. It's not too bad. It's not. They're just bits. It's just for loops.
Just the visual of you saying it's not too bad, and then you click a button, and it's like the whole screen is filled with numbers doing a lot of different things.
Yeah.
Is really, really fun.
It's 32 bits, 64 times. That's all. Oh no, I had fun working on this.
It's just fun.
It's okay. All right. Is timing good? Oh, thank you for whoever's putting things in Discord. Okay. Message schedule array, working variables. The working variables essentially cycle with just a little bit of fiddling with the bits. And over time, you slurp one each of the elements of the message schedule array into your working variables. That's all. It's just loops. This is not actually, I don't know how much this will help you. Look at it if it helps you. Okay. The endianness on this is wrong, so it doesn't solve the only hard problem. Okay, that's all I have. Any questions other than like, why? Because it's cool. It's cool and fun and good. Sure. Yeah, so this is a problem I haven't figured out with the typesetter. I can't figure out how to specify the apostrophes I want.
Yeah, well, you can use like a active instead of a single quote.
In the source code? Okay. So sort / There's like a neek right there, right? So I'll be able to find it quickly. And so our thought is that should be, what was it? We think it was that, and that it should be this?
Yeah.
Okay, cool, good catch. I was having a time with these on the Turing machine slides. I could not get them to work.
I have no idea. I think I'm close to understanding the rules. I mean, that it's a long
That is